Hey, thanks for joining me today. Welcome to my channel. Thanks to those who like my videos and gave me feedback. Thanks for your encouragement. For those of you who have some questions on what I explained, or if you didn't get the way I explained, or maybe I didn't touch the details enough, feel free to ask me about those in the comments. Sometimes it's hard for me how deep I go or how basic explanation I give. I just have to look at the compromise between, okay, I don't go too deep, but at the same time go enough that if some people are new, they are able to understand the remaining part of my video or remaining part of my lectures on physical design. But you all are welcome to give me any kind of feedback that you want. If there's anything you want me to improve, I'm open to that. All right. So with that, let's get started. In video 3 on system on chip, I gave a step back to what I was explaining in video 2, and I gave a higher level overview of what is system on chip, what is physical design. um, and I believe with that information of higher level, um, now you're able to see why I was going into basic cells, basic gates, information in video 2. So today will be a follow-up from where we left in video 2. In video 2 I bent over what is inverter, okay, what is AND, what is NAND. So we were looking into the basic gears that are the basic building blocks in physical design. So let's move on. I think one other basic cell that is worth mentioning is a NOR and R. And what happens is the symbol for NOR is, all right, that's good. Okay, and the symbol for R is this output. Okay, in terms of the table that I also shared for NaN, so the way this NOR transform the information is, if let's say A, B, and we have 0, 1 for any A or B, so we can have 4 combination, 0, 0, 0, 1, 1, 0, 1, 1. Okay, the NOR, let's put R, that's how I remember it. So characteristics of R are that once one of the input is 1, okay, output be 1. So you see 1 here, this is 1, 1 here, 1, and both are 1. And when both inputs are 0, then output will be 0. NOR is the inverted form of this. Whenever both inputs are 0, it will be 1, and when either of those is 1, it will be 0. Sorry, I don't know what I said. So 1, and then remaining times 0. Okay, and how we achieve this? So I'm going to look into, like I look into NAND, I'm going to explain NOR here. So if you remember, in case of NAND, we had 2 PMOSes in parallel and 2 NMOSes in series. And NOR is the opposite of that, and you will see why. So here we have 2 PMOSes in series and 2 NMOSes in parallel. Okay, so A, B, let's say same is connected here, and B is here, like let's say same B is connected here. Okay, this is the output. Okay, and you can see that the PMOSes. So in order for this node to go to high voltage or 1, both of these PMOSes need to be active, need to be on. And we know that PMOS is on when input is 0. Okay, so when A is 0 and B is 0, output is 1, and which you can see going back to this when both input are 0 up to 1. And when either of input is 1, okay, that means one of these PMOSes is off. This node won't be able to go to 1. And on the other side, for the two NMOSes, they are in parallel. So when one of them is 1, input is 1, and that means either this is on or this is on, the output node will go down to 0. So this shows you that this behavior of R0 when either of input is 1. And R is as the invert form of NAR. For example, if they add the output, we put second, all right, that's good. Bigger. Okay, so if I put inverter here, okay, the symbol for inverter is, if just as a reminder. Okay, so once I put an inverter, and 1 becomes 0, 0 becomes 1, 0 becomes 1, 0 becomes, so this together, this circuit is an R, and just this is a NOT. Okay. All right, let's open together. So far what I have shown is the functionality of, let's get back to red, inverter, buffer, NAND, and NOR. Okay, R. And these are inputs, and this side are outputs. Okay, so you can see that whenever input changes, output will change. So in this circuit, there is no concept of storing a value, or there is no concept of memory. And we know that for an intelligent system, okay, we need to time the operations. Okay, so we want to do maybe first inversion and buffer or AND. We want to keep the output, and based on that, we want to do some more functions. So here, if you put, for example, another OR gate here, again, same thing will happen. Input will come, output will change. Now, when the input comes, output comes, the whole change doesn't happen instantly. Instead, it happens with a delay. So, for example, on the input side, let's say you have input. Okay, again, your input will not be instant from 0 to 1. Instead, it will make a transition and with a certain delay. So this, maybe I should explain this later, but the time that it takes from this 0 to 1 is called transition times. And similarly, let's say this was our input, and our output, let's say it was a buffer, so input is same as output. It just delays it a little bit. We know that it will take for transistor to switch on, there will be a little bit delay on for the output to change. So output will come something like that, and um, this time difference between the middle 50% of the value of input to the 50% value of the output is a delay, propagation delay or delay. Okay. So going back, what I was saying, information on these cells, which are called combinational elements, flows quickly, and there is no concept of storage there or memory there. So in order to have a system more intelligent, we need to add um, times, timely operations, and for that we need to store the intermediate values of different nodes here. So what we want to do is, for example, we have an NAND and we have an inverter. They two together, they become an R. And what we want to do is we want to store this value for a little while, and so that our next circuit that's happening, there's another value that's, so we want to this output O2 and this is output O1. What we want to make sure is O2 happens after some time, because we know that A, B, C, when they are changing, we don't want to use their values at the O2 quick immediately. We want to wait for certain time, and the way in we time these operations in digital circuits is by using clock. Okay, so you have seen that in every digital circuit, clock is a fundamental element. A clock is something which go to 0, 1, 0, 1, 0, 1 with a certain period. The time that it takes from here to here for one complete cycle of 0 and 1 is called time period. And the inverse of time period is frequency. You already know that. Okay. So what we want to do is, for example, in this cycle, we just want to make sure only this operation is working, and during that time, the value here on the, let's say D1, it doesn't change with A, B, C. Instead, D1 keeps its previous value. Okay. But the storage element that we can use for that operation, for that memory operation is, so these are two. One is latch and the other one is flip flop. Okay. So actually there's a third one too, which we call memory, on chip memory, which comes in the form of SRAM, okay, ROM, or register files. Okay, so I will go into a latch again, and just for the sake of understanding the basic functionality. Then flip-flop, I don't plan to go into too much detail of SRAM and ROM. These are the larger circuits. Maybe I'll do another video on those, but the whole concept is you have the capability to store a very large amount of data. You can store 1 bit for one latch, 1 bit with one flip-flop, and I'll tell you what's the difference between latch and flip-flop, but the memory can be used to store much bigger data. And typically in physical design, if I am doing a physical design of an IP, and as I mentioned earlier, an IP has analog and digital portion. So let's say I'm doing physical design of a digital portion. Then if I use on-chip memory, because the way RTL folks wrote RTL, they rely on storage of large amount of data. Let's say, for example, the architecture works on packets. So when the input packet comes in, and let's say it's a networking application, all the packets are stored in the memory, in the main memory, okay, of the system on chip. And a CPU, or let's say an accelerator, wants to bring that data, small chunk of that data, and stores it locally, so that it doesn't every time doesn't have to go back to the external memory, because external memory access will take time. So locally you want to store that large chunk of data, and for that purpose we use SRAM and register files and ROM. So I'll mention maybe in the next video what's the difference between the three, but let's focus on latch and flip flop today. Okay, so latch. Both latch and flip flop can store a logic 0 or a 1, and as a combination of those they can store several bits in the design. What is the basic storage element? So let's look into that circuit. It has an inverter, two inverters connected back to back. Okay. The beauty of the beauty of this circuit is, if somehow in the input we are able to write 0, okay, once we have 0 we'll go to 1, and once this goes to 1, which means this is 1, this will go to 0. So, and you can see that this circuit will keep that information. Let's say this was our output. Okay, and once we are able to put a 0 at the input of this inverter or output of this inverter, this output will not change. Okay, so it can store that information. But the important thing is how to write that value onto this node. Okay, because once we have written 0 or 1, the output will hold that value. Okay, so that means we can connect it to input. Okay. However, if you you notice that if I do this, then whenever input changes, let's say input is 1, this is 1, this is 0, this is 0, this is 1. This is not a storage element anymore. Whenever input changes, output will certain delay and not a cycle of the clock. Okay, output will change with a little bit delay, but it doesn't look like a storage element. The storage element this becomes when we are able to control the input. When we say, okay, let's take another color. So let's say this is our clock. When we say that during this, when the clock is high, this is 1, this is 0, we can store the information. Okay, and during 0, whatever information that we previously stored is maintained on output, so that the circuits which are after this, they know that, okay, whatever input came in the first half cycle, in the second half cycle that input will not change. Okay. So how can we accomplish that? Let's look at this. What if we put a switch there? Okay, so when input is say 1, we write the data it turns on. This is like a clock. Let's say CLK. When input is 1, this is switch is on, and we really close this circuit and we are writing this data. Okay, but once we do that, this input will change, output will change immediately. Okay, but what we want to do is we want to make sure, wait a minute, so let's add another. Let's add another switch there. And let's put an inverter here. So when input is 1, clock is 1, this is on and this circuit breaks. So we don't have that storage element. Output follows the input. Okay, so this input goes there. And this one is broken, so we are not overriding this circuit. So 1, 1 to 0, 0, 0 to 1. So if input changes, this output will change without this node overwriting the delay of the previous value. So input is 0, output is 0, input is 0, output is 1, and input is 1, output is 0, and we know output is inverted, but still we have a path from input to output. Let's see what happens when we are in cycle 0. When cycle 0 happens, this becomes 0, that means this turns off. And when this is 0, this is 0, this is 1, this is on. Okay, so now we have this thing completely disconnected, and we have this thing connected. So now it acts as a storage element. Whatever the last information that we wrote on this node, this circuit will store that. So during 0, our information of the output doesn't change. Now what you have seen that it's important that when this was when clock was changing from 1 to 0, and we know that the change will not be abrupt. There will be a little bit time in reality between 1 and 0. What we want to make sure that when this happens, the input data, certain time before this and after this data doesn't change. Because during this transition, if this input changes, we might get a value written on this node that we don't want. So those numbers are called setup and hold time. Okay, if the time that before the edge that we need to make sure we don't change is called setup time. And the output that after clock went change the level, we still want to make sure that we have this time over here, data doesn't change, so that will be called hold time. All right. And this circuit that stores the value that has the property that is transparent during 1/2 cycle. During that half cycle, it's sampling, and during the other half cycle, it's holding. Okay, this is called latch. Sorry, and its notation is this. So this one, as you've seen, this is when input is clock is 1, it is transparent, so it's a active high latch. And when it is transparent during the negative cycle, okay, we call it low latch. The other circuit, now look into, by the way, I forgot to mention one thing. When I put these switches, um, and what's the best switch? It's a transistor. So you can consider these switches as, let's say, an NMOS we put. Let's put the other way around. Okay. The other storage element that we need to talk about is flip-flop. Let's look into the overall functionality of flip-flop, how it is different from latch. Let's say we have our favorite clock. Okay. And we have input, output. Let's try input with, think of that now. Let's say input was some value D1. Okay, I'm putting D1 because in this form because it's a little bit easier to explain instead of 0, 1. It changes to a value D2. So how the output will look like? Okay. So the output in a flip-flop changes only at the edge of clock. The edges are, okay, this is falling edge, this is rising edge. So low edge, high edge. So in this example, let's say it's a flip-flop which changes its states at the positive edge. So in this case, as I said, flip-flop changes its output only at the positive edge. So after the positive edge passes, what value flip-flop will have? The flip-flop. Okay, D1 or D2? Okay, the correct answer is D2, because it really matters what was the value of the input data at that edge. Okay, that was D1. Now look at the same thing from a latch point of view. So let's say it was active low latch. Okay, so active low latch is output will change only during the low cycle of the clock. So during this one, this is transparent. Okay, so whatever is input, the output will become like this. So this is latch output. So it will be some portion of D1 and D2. So you've seen the difference between the two. Flip-flop gives us a cycle where it stores previous value. Latch, half cycle. They both have pros and cons. Maybe we can look into those in a separate timing analysis video. For flip-flop, okay, the important thing is, as I mentioned before, for a latch, setup and hold time. Okay, again, the clock is in the real world is not ideal. Okay, clock will have some delay when it moves from 0 to 1. Put it blue there. Okay, and it's important that during this transition of clock, the input data that we don't want, that we want at the output, doesn't change. Okay, so there is a time interval before the edge and after the positive edge. Okay, during this time we don't want input data to change, because if it changes, we wouldn't be sure the output takes which value, the change value or the previous value. Okay, so these times again, in the case of like we had before, setup and hold time for latch. So flip flop, the time just before the active edge, this one is called setup time, and the time right after the clock is called hold. Okay, so data shouldn't change during setup and hold time. And I will look next into the structure of flip flop. Okay, I think we probably should stop this video here. On next video, we will start with looking into creating a similar circuit that I created for latch. Let's look into how flip flop is different. Again, for a physical design, you don't need to understand the whole inside circuit of these basic elements, storage or combinational. But understanding of these things helps you better understand the high level concept. So what is setup time, what is hold time, what kind of delays involved, why flip flop is bigger, what will happen in case of latch and flip flop, what are the area differences, what are the timing differences, what would be good for me when I have a design with flip flop or latch. So that's why I'm spending time. So our foundation is good, our understanding of the basic element is good, and then next level, when we are playing with these standard cell building blocks, it will be much easier. So let's stop it here. Next video I'll start further details on flip flop. See you then. Thanks. Bye bye.